Yeah, welcome to Mastering Distributed Systems from Unreliable to Resilient. This is actually the, well, condensed version of a workshop that was running yesterday in the very same room, funny enough. But yeah, we'll see how we get through this and how much of a eye-opening or maybe not eye-opening thing that is for you. So, hi, I'm Arne Blankerts. I'm helping teams to write better software, write the more stable software, write the right software, as in create the software they actually need to solve the problems, and not necessarily follow the latest cool hype thing just because it's cool. And it was a fun experience yesterday when we did the workshop edition of this, that everybody was like, yeah, but if we do this way, it's not cool, because it's boring old technology and it's concept that we already know, maybe that we should have been applying, but we got distracted with having like new fancy other things in place, and for whatever reason figured that might be cool to use that one. So let's start with a nice kind of atmosphere for everybody. So in the beginning, chances are you had a monolithic kind of application, or maybe even still have, and everything is fine. It just works, everything is cool, you're successful, and at some point you realize, well, maybe we have more requests than the single system can actually handle, and we actually have to start to scale out. Or somebody went to like a conference and learned cool object-oriented kind of cool things, and we need to like change our software just to be cool and make it look nice or have it structured better. So people are like, yeah, actually I can see what this piece of code is doing without being distracted with all the tiny details that are implemented. Usually that's a service-oriented kind of architecture that people like a lot because it makes sense from a business reading perspective. You can look at the code and can say like, yeah, do this, do that, makes sense. I don't actually need to understand at this point how this exactly works, but I just need to understand the full flow, the actual business process that's supposed to be implemented. And there's a lot of value in that. Given that in many cases, particularly in legacy kind of applications, we were used to creating like long transactional kind of things that did all kinds of cool things, but they mixed the syntax of the programming language of choice and templating and like visual other aspects with database queries and logic and everything in one. So there's a lot of effort required to understand what the actual business requirements particular software used to be, or maybe still is. So moving this into like nicely encapsulated kind of things is probably pretty helpful in understanding and maintaining the code. But of course it comes with additional problems. So let's look at the traditional approach of what we could potentially be doing, or might have been doing. And my standard example for all these kind of things is a sort of kind of e-commerce-y kind of thing, because for whatever reason, in the web environment, many people do things in this kind of field. So the majority of people either work in an environment where e-commerce is a thing, or have used any kind of e-commerce platform themselves in their personal life. So everybody has a general understanding of what this is about. So if we have a traditional kind of ordering system, chances are if you have everything backed on a single database, like the global God kind of thing where everything is in, if you want to make Oracle and friends happy, this is what you like, then you usually start with a transaction because you learned, maybe even the hard way, that doing various SQL statements that make writing changes and then suddenly crash intermediately, having the previous like 1, 2, 3 things already persisted while the next one is missing, causes an, well, not necessarily happy state to be in. So you use a transaction. So you do something, you write an update to something, and then yeah, everything is cool, except when you now have to talk to an external system in between, like called to Stripe or some mail sending service or some other request thing that you need to talk to. And yeah, what happens if that fails? So now you're in the middle of it and everything is cool. So we're here now where the red thing is, because we're in a database transaction, right? So if this fails, we just do a rollback on the database and everything is cool. But if we have more than one thing and have more things to do here, well, now this already happened. So how do we make this unhappen? And that's a problem, because relying on an external system, as helpful it is to not have to implement everything yourself, means that you actually have to rely on the fact that the network is going to be there all the time. And maybe in some environments you can almost certainly guarantee this. Like Facebook, for example, claims that at some point in the past they actually changed the TCP stack of the Linux kernel because they can guarantee certain kind of performance things that the kernel usually tries to like have fallback mechanisms for. Well, if you're not Facebook, chances are that's not what you can do. So if you have to talk to an external service, external meaning it's something that's not running in the same process, that could even be on the same physical device, just using a different container, which is usually networking, or it could be a socket and the process just died, which is technically also seen as a kind of network in that case. So chances are network's going to fail, that service is not reachable, and now stuff breaks. This might not necessarily be a common scenario, but chances are it's going to be common enough the more requests you have. Like the likelihood of a failure increases the more times you use something, or the stronger you're dependent on it. So assuming that you've been trying to send out an email, and at some point you decide, okay, we're going to send out the email now, and then I'm going to tell the other thing to do something, and I can't reach that thing. So doing a rollback on the database transaction is easy, but how do I unsend an email? Well, if you're using Outlook, you get this, or Exchange, you get this like this user wants to pull back that particular email, which nobody else supports, but maybe in that scenario it might actually even work. But for the rest of us, usually it doesn't. So now we have a problem, which in most cases people try to recover from by using something which is called a two-phase commit. And I'm not saying this is the only solution, but it's the most common one, that if you look around, like, hey, I have to do this external kind of thing and I have to do various things. I cannot rely on database transactions. What do I do? Then the most common answer, also by Google LLMs and all kinds of things that you can ask for, is like, yeah, use a two-phase commit. That's the standard way of doing it. So what's this two-phase commit kind of thing? So that basically means that in our example here, we have the order being placed, and we want to reduce the stock. So we want to make sure that we have whatever amount that has been sold is going to be taken from the stock. And we, of course, going to get paid for it, right? So we have to talk to the payment service as well. So in a two-phase commit, we're going to tell the stock service, like, hey, prepare this kind of operation. I want this to be removed at some point. Please do everything that we would need to do, but don't actually fully commit it yet. Just prepare it. Then we're going to tell the payment service, hey, please do exactly the same thing. I want to capture money at some point. Please make sure that we have everything in place so that I can actually tell you, like, now is the time to actually claim it. That's kind of a standard thing you might be seeing as well. If you pay with a card at like a shop or so, then you see that if you scan it or tap it, then the money is captured, but it's not directly booked off of your account. It's going to take a bit of time because it's a, well, period of time that actually completes. Same thing if you are implementing any payment APIs in your actual software, chances are that you're going to capture the money as in claim, this is money I want to have. All the checks will be performed by the payment provider, and they give you basically a transaction identifier back where you can say, okay, everything concluded here successfully, now you can actually charge the customer and transfer the funds. So that's the two-phase kind of things that happen. So we can do this here, we can do this here, then we do whatever else we want to do inside, and if everything worked out fine, then we tell the individual service that it now can be committed. Does that help? Looking at this, it seems like it makes sure that this is actually doing everything we need to do. This can do everything it needs to do, and at the commit part, we just basically set a flag. So that cannot be that hard. And yes, technically it can help, because if we do this commit now or in 20 minutes, it's not necessarily a problem. It just takes longer until we have the stock reduced or until we have the money on our account. But if we have this thing only do something in memory and not actually persist this in any way, if this thing crashes in between, that transaction information is gone. So that's a problem. So it has to submit it and store it, but consider it like semi-taken. So if I have a stock, then obviously it's reserved, I guess. But for how long do I keep it in this reserved state? If you book a seat at like some conference or a concert or theater play or in a cinema or so, chances are if you do the online booking thing, they tell you like, hey, we reserved this particular seat you selected for the next 10 or 15 minutes. This is technically a two-phase commit, right? You're writing directly, hey, this seat is semi-taken, but it's not really yours until we actually commit it. But nobody else can get it either until either you committed it or the timeout occurred. So that means it's blocking, right? Because this particular thing is in a state where we do not necessarily fully know, but for paranoia reasons, we're not going to allow this to be used by others. So in an e-commerce site, you could create various checkout processes, and with that, basically exhaust all the stock that you have without ever finishing it. So you can't sell anything because it's reserved all the time. That's probably not what you like. And of course, it's blocking because unless you have this short timeout period in place, somebody needs to clean up in case this thing actually crashes or this commit never happens. The database transaction will just roll back at the end of the connection. That's easy. But then you have an inconsistent state because this thing worked and this thing didn't, then you're basically back to square one. So short answer is probably it doesn't. At least in most cases it doesn't, because this blocking attribute is something that's, for scaling web applications, a serious problem. So maybe we have to think in a bit of a different way. Let's go back to the beginning, not of the full talk, but like from our way of looking at things. And one thing that might be becoming obvious, if you think about it a bit, is that what we tend to do is we mingle the decision with the side effect. So the business decision, like, hey, this has happened, this is okay, and then something else has to happen because of that, should not be the same thing, and it should not necessarily happen at the same point in time. Because if we separate the two things, then, well, I guess solid for the win, single responsibility, doing one thing at a time and doing it properly, helps us a lot in getting stuff better and making things easier. So if we were to separate the decision from actually having side effects, we are almost talking about events, right? So we have an order service which emits an order placed kind of event and just puts that into the event bus. Which means at some point in time between now and never, some service is going to pick it up and do something with that information. So we can have the stock service handle this particular thing and reduce it whenever it is available. Now that means we are eventually consistent. Yeah, I'm going to go to that in a second. Right, because if the order has been placed, the stock information has not been updated yet. This can be awesome because we actually don't really care. And we're just going to make sure that we're going to sell things as much as we can. And if the stock is really low and then somebody is the last one, well, then too bad. And the funny thing is, at this very conference a few years ago, we talked to people from Eventim, like the company doing all the ticketing for concerts and everything. And I told them that I was trying to get tickets for some concert for a friend of mine. And I only got like white pages without anything on. Yeah, that's our fail page. Okay. Yeah, we don't care if it's broken. Like, huh? Why? Because the concert is going to be sold out in the end. I don't care if you get the ticket. I care about the fact that all tickets get sold. Who the individual buyer is of no interest to Eventim at that point. Yeah, I can see that. I mean, they changed that by now, but there was still like, okay, there's no business motivation to fail nicely if everything is going to be sorted out in the end, and whoever gets the last ticket got the last ticket. Maybe you have to say sorry, and then here's your money back, but okay, maybe that's easier than trying to be consistent all the time and not have other scaling problems with that. So if we're going to do this kind of thing with an event bus, that of course doesn't mean we have to have like the big queue like Rabbit, Kafka, whatnot in place. You can do this in memory or within an application or in a database. There are many easy, small ways of implementing this event bus kind of thing. But in general, we now have a technical problem because most people, while they like the idea of having like an event to tell others that something has happened, they also want to have a local persistence of the thing. So we're going to have an order table where like the traditional relational, maybe ORM mapped kind of thing, is being stored. So that means we have two writes, right? We have to run one write to actually store that particular object, and we have to create that entry in the message queue. So if we decided that we're going to use a message queue, that's an external system. We're going to store something in our database where we could potentially use transactions for, and we're going to talk to an external service, probably via HTTP. And yeah, we are back to square one because we're talking to two systems. And the fact that we can write the message into the object into our database table, okay, that worked. Now we are trying to write that event into the event queue. And because the queue is not available for us, network fail, whatever, we can't do this. So how do we recover? We have an order being stored, but nobody knows about it. So that's not helpful. Then you could say, okay, let's do it the other way around, right? Let's try to write this to the queue first, and if that worked, we're going to persist it. So if you now have a message being sent to others about an object that you didn't manage to persist because for whatever reason the database is not reachable, it's also not very helpful. So we need to figure out what to do if either of the writes will fail. That doesn't happen all the time, of course. It will just happen eventually, and it's going to be a pain to debug because somehow one order is missing somewhere, but it works for 99.9% of all cases. You're not ever going to find that, at least not easily. So the common answer to that particular problem is called outbox pattern. So that means we are going to do two writes in a database. So it's an atomic operation. So we have a transaction, and the order service creates whatever entry it wants in its order table, so its local persistence mechanism, and it creates whatever message and stores it in an outbox table. And you can literally consider this as the same kind of process that you might have in a traditional office, particularly in larger entities, where you have like this out mail box standing on your physical desk, and at some time during the day somebody comes by, puts new mails in and takes the other one and then distributes it around. And you don't actually have to care about how this is being taken from there. It's just like, okay, you did whatever you wanted to do and put a copy in this particular outbox thing. Given that this is in a transaction on that very database, this works like the traditional way as we had before. We just now need to add additional complexity to actually get this thing relayed to the others, right? So we need a process that now reads this from the outbox and puts that actually into the message queue. So that would potentially look like this. So you have the new additional relay process. So you realize we made this stuff more complex, right? So we didn't actually just only make the software potentially more reliable. We also added additional complexity. Whether or not that's worth it, we actually have to see in the end. So this would be an external process that would read from this outbox table and then just forwards this in here. So this is basically a 2 or 3 line application, right? Connecting to the database and pulling in a loop. Whenever there's something new in here, we're just going to forward it. And this can be also an external thing that actually looks at the replication log of that particular database. For example, if you have MySQL in place, then MySQL creates a bin log for all the transactions and all the things that need to get replicated to other servers. So if you have like multiple databases and they need to replicate data around, and you can have this process monitor this bin log and use that as the outbox, and then forward that from there, because it's a raw entry which is supposed to be like the message that you want to get distributed anyway. So it's going to forward it without actually doing the additional outbox table per se, but the concept is the same. It just uses the bin log as the outlog table. So that's cool. Now somebody else can pick this up and do something with that. So there's a problem, of course. I mean, why wouldn't there be, right? I mean, we came up with a new cool solution, and of course, new solutions always have new problems. And the first problem that comes to mind here is the at least once delivery, which sounds pretty awesome because it guarantees you that the recipient, in this case the message queue, will have it at least once. It also means that the recipient on the other side of the message queue is likely to have it at least once. Well, that's cool because we know the message is not going to get lost. That's quite different to, for example, PubSub kind of environments where usually you only get a message while you're actually actively connected, and if you disconnect, then, oh yeah, you're not there, I can just throw the message away because nobody cares for it. So in this kind of scenario, we have a at least once delivery. But at least once means duplicates are coming, right? Because it can happen that we're going to get this sent twice. So for this logical thing to work, this particular process needs to read from here and figure out like, hey, there is something new. But how do you determine that there's something new? By having some sort of marker, either mark that entry as being processed or having a local memory saying, okay, I've been processing till timestamp X or to ID Y or whatever other identifier you might have to know in the table where you left off so that by the next time you run and look, you can see there's actually something new. And then you actually have to send it, and then you have to update that particular pointer or mark the entry. But that's 3 operations, right? I have to read, I have to talk to the other thing, and have to mark it. So reading, let's assume that works, because otherwise we didn't have anything to do. Then we're going to send it, and then we crash for whatever reason. So the marking didn't happen. So the next time we start, we're going to read again. We're going to read the same entry again because we didn't mark it or update our pointers. And now we're going to send the same message over again. So there's no way to avoid this from actually happening. And while there are systems that claim you can configure the exactly once thing, they cannot really ensure that. There's no physical way of doing this. You can make it very, very unlikely by memorizing all kinds of things and having all kinds of checks in place. But there's literally 0 way of making this completely go away. So we're going to have to deal with duplicates. So to make sure that we at least realize that we are getting a duplicate, there's the logical counterpart of the outbox, which is the inbox. So the message queue got the message, and let's just assume for now, for the sake of simplicity, it doesn't really care whether or not it had this very message before or not. It's just going to forward it to the potential recipient, in this case the stock service, and the stock service will have to have an inbox table where it basically has to store either the full message or just the identifying attributes for it, like the ID, any unique identifier that you can come up with that makes this particular message identifiable. And if it realizes it has seen it, it can just discard it because it's just a duplicate. And then it's going to forward it to do the external action. So that's not, of course, solving the problem that this external action can still fail. But that's a different problem. The only thing we need to make sure in this particular concept here is that we do this update here first. So if the message comes in, we're going to try to store it in this particular index table. And if it fails because it's a constraint violation, then we know we have already seen this, and we can just discard it. If it fails because we can't talk, we just not acknowledge it, so we're going to wait for the queue to send it to us again. And if it worked, okay, we now know it was a new message, and we're going to forward it to this particular process. And if this process can't handle it, well, now this particular process needs to do something, like raise an alert, write it to somewhere like, hey, I couldn't process this particular message, or whatever kind of meaning you have in there to actually make sure that this actually, well, gets notified to somebody or noticed in any way. But the message forwarding thing at least is sure that we only have at least exactly once processing on this particular thing here. Of course, you can make this more complex, but you get the general idea, I guess. So, cool, everything works, right? Mission accomplished. We have a stable system, we can update all the cool things, and then reality bites. Because, I don't know if you ever had that, but I had that particularly when there's like a low stock quite a few times. Like you check on the website like, hey, yeah, this store location has one item left of this. And you drive to the store like, hey, I want to have this. Well, shelf is empty. But yes, yeah, not there. So stock says we have 10, but yet the shelf is empty. This is not a technical problem, right? I mean, the fact that the actual stock does not fit the perceived reality from our data store is not a technical problem. Maybe it's a process problem because somebody managed to somehow not update things. Maybe it got stolen, so the system couldn't have known. Maybe it broke when somebody was trying to put it in. Whatever the reason, that's why supermarkets have the people counting things every now and then to verify that the perceived stock and the actual stock are actually in sync. So this is not a technical problem, and this is thus not requiring a technical solution per se. It requires a process solution. But of course, that means for our software, we are not done yet, so we have to continue developing things. And we have to come up with a solution for that. And the standard answer is the so-called saga pattern. The saga pattern basically is a fancy way of saying we have a business process to deal with all kinds of things that could potentially happen and go wrong and come up with a correct countermeasure. So that's like if you do any type of bookkeeping, you cannot pretend a booking didn't happen. If you don't like it, you have to come up with a counter operation. So if you send out an invoice and the client says, wrong, well, then I'm going to cancel out the invoice. You cannot pretend the invoice has never been created. So this is exactly what the saga pattern is about, trying to think of a workflow. And okay, if this breaks, then we have to track back and undo all the things. Of course, there are things where you cannot technically undo it. You have to do something that maybe says sorry or whatever. So the so-called compensating transactions for like, okay, we try to sell you this item, we already got your money, we already sent you like a message, everything is cool, but then we realize actually we don't have the item, so we can't ship it. Well, then you have to apologize and refund. That might be an option. Or it's a apologize, it's going to take a bit until we restocked because we're waiting for incoming stock. Whatever makes most sense in your business case, right? So to do this and to implement this saga, we have many different ways of doing this. And the most common two are either the orchestration one that I'm going to show first, and well, I'm going to show the other one after that, so not to distract you too much. So orchestration is like literally like a concert. So you have an orchestra, and you have the conductor staying in front, and the only person, well, probably not in reality, but at least in theory, who knows all the music, as in all the notes for all the instruments, is the conductor in front. Everybody else knows their part. Like if you're playing the violin, you're going to have the notes for the violin, not for the trumpet. I guess that kind of makes sense. And the conductor is going to tell, okay, you start playing your part now, and then you start now, and now you start. And okay, now you're done, now you can play. Right? So this is the conductor kind of approach. So in software, that would look like this. We have the order service emitting our order placed event, which is cool. And it's going to be sent to an event bus. And our conductor box here listens to this and tells like, OK, given that the order has been placed, I have to reserve the stock. And basically tell the stock service, hey, please reserve the stock. And if that worked, it will return a stock reserved event back into the event bus, which the conductor is going to read and then tell, OK, actually, that means I actually have to capture the payment now. So payment service, please capture this. And it will return the captured event and so on. That's probably pretty readable, because it has one single piece of software that knows about the process. So this is a kind of centralistic approach. This conductor is the God instance of this particular process. It knows what has to happen next, given a certain event had shown up. Which is good and bad, of course, because that means that you actually, if you want to change the process, you actually have to change the implementation of this particular class, which usually we are not necessarily afraid of, but of course it means we actually have to change working software. And one of the promises of object-oriented programming, at least back in the days, was that if you want to do different things, you should be able to write new software without modifying existing software. Well, if you have one single class doing this and reacting on all the things, then you have to change this. You can, of course, break this down and have individual handlers. So like this is one that reacts and does this. This is one that reacts on this and then does this. So it's just logically grouped, but it's still individual classes. That just means that the process that handles the event stuff needs to call different classes to do the individual thing rather than one. Then we are a bit more flexible in that regard, and we can just add new and remove elements if we don't want this particular way of handling this type of event any further. But of course, that moves the knowledge outside of the individual components, which can be pretty good or exactly not what you want. So the alternative is to have a choreography. So that's literally like the dance. So imagine like a theater show where like dancers are on the stage. While everybody trained together, of course, there's nobody telling you, OK, you start doing your routine now. Everybody knows, OK, this is the beat, and I know to do this now, and I'm going to do the next move now, and I'm waiting for this person to pass by so I can do this step and whatnot. So everybody knows their own routine and reacts on the things that happen around it, basically by listening to the music or by other people doing things. That could then look like this. And you can see this is a lot less code because we don't have this command thing happening at all. We only have an order service that places an event into the event bus, and the stock service reacts on like, hey, cool, there's an order being placed. That means I have to do things now. And it's going to emit the stock has been reserved and writes that back to the event bus. I'm done. And that means that the payment service now like, oh, stock has been reserved. Cool, now I can capture actually any funds. And I see some people like, wait, what? And that's exactly the question that you have to ask yourself when you do it like this, because that now means that the payment service now has to know that something like stock exists, which probably is weird. So you could say, OK, you know what? We're not going to do this when stock has been reserved, but when an order has been placed. So we do these things in parallel. And then we have some other process that has to wait for this reserved and this has been captured. So you can change the design on how this is going to be, well, looking together and waiting for various things to happen and then continue from there. The only question that you have to answer yourself is which one to pick and which one you like better in your particular environment. The answers are you're going to end up with a mix of the two things. So sometimes you're going to have a service that's going to emit an event, and you're going to handle that event internally as well. So for example, if the order service creates this order placed event, then you might have an order service related event handling that will create a projection, render like some nice HTML page or fragment for like this particular order, just because that belongs to the order. Or you have the payment thing do something else with the event that is actually being captured. Add some statistics, counting, whatever kind of thing that you consider relevant that is, by your definition and decision, part of that particular service. But for others, you might send this around. The funny thing is, wait, I was too quick, that using a command to this is just another means of having another layer of indirection, because you can put this in a command queue, right? So this thing is not actually doing anything except dealing with the process. That's where doing something like this is, like with N8N, for example, as one of the management tools that's pretty popular these days, where you can define workflows. It's like, okay, this happened, then make this happen now. And it doesn't actually have to do it itself, it just has to write the proper command to somewhere, and then some other process is going to take care of it. But you can, of course, also do this in process, so you can make it a synchronous kind of thing, trying to just call this as an API method, because obviously this is the command that you could also create as a method in that particular object, and you don't actually have to do this to an external thing. The most relevant part is that you don't do everything in the same process, because then you have basically the same thing again, that if something gets stuck somewhere, you don't know where you left off. Or you could get away with some means of recovering from that, but that's making things more complicated anyway. So, which one to pick? It's up to you. I usually like this kind of conductor approach because I'm a fan of having like a single place where everything is written down. But I've also created software for teams or with teams where we decided to follow just listening to events. And sometimes we even duplicated the things. So we basically decided, okay, this event happened in this domain, and we're just going to forward it as a different type of domain, basically translate it so that it's becoming information to the outside, or it's aggregating various events together and then creating a larger domain event for the outside. So this, of course, is very much simplified to actually get going. So I guess the key message of all these things with distributed systems is that the more you distribute things, the more likely it is that something is going to fail, just by the bare nature of having more running pieces. And of course, something can go wrong somewhere. So let's make sure that we know and design our software for the fact that things will fail, and we need to recover. And we need to be able to make sure that we lose basically zero information. So if we store stuff as early as possible, and we have a means of realizing like, hey, we stored this, but then nothing else happened, we already won. Because we cannot prevent things from failing, we need to be able to see it, so it's a monitoring question. And we need to make sure that when things break, that we, well, have a means to recover from that particular break. And with all the things I showed you, you have a means to recover, because you can realize like, hey, there's a discrepancy between like, hey, we have so many orders, but only so few entries in the outbox, something must have gone wrong, even though technically with a transaction that shouldn't happen. Or we can realize, okay, we didn't actually push this yet, or there's like so many entries in the outbox, but our counter where we actually left off is way behind that. How can that happen? Well, maybe the relay process crashed. And well, that's what monitoring is for, right? Thank you very much. We have, I think, 5 minutes for questions and comments, if there are any questions. Otherwise, we have an early break. Yes, the question.
What happens if the event bus fails?
What happens if the event bus fails? That's a very good one. Let's go back to some of the drawings. Let's take this one as an example. So, okay, so this one wants to emit this, but can't write there. Okay? So, how would you get this event from here to here? Well, the standard answer would be, here is an outbox first, and you have a process that tries to write it to here. And if that process can't write to here, well, then it can't do this, but nothing actually happened because the information is still here. That's exactly the same thing you would have technically with your mail server. If you send the mail to your mail server, well, it's stuck at your mail server if it can't reach the server it's supposed to send it to. and will just keep trying until that server is back up.
So in this diagram, I should imagine that each and every emitter has an outbox.
Or has a backup mechanism to store it, and then go back from there. Yes. Okay, another question.
Thank you for the talk. And as I understand the general idea that if we can't perform one process atomically, we need to split it into a workflow, a state machine, and make sure that every state can contain, can store its current state and restore in case of failure. So
Yes, pretty much. The biggest problem, I saw that, the biggest problem with distributed systems is that you have to get stuff moved to the next thing, which is somewhere. And somewhere means not in the same physical process memory scope. So if I have a chance of this not working out, I need a mechanism to store that state if I think it's important enough to be kept. And so I can recover from that and, as a matter of fact, do this after the fact. In some cases, this is completely useless. Like in many cases, if you have statistic software, well, if I can't write the statistical data, I'm just going to discard it. I don't care, right? Then you have like a empty spot in the graph, but that's not necessarily a major business impact for many cases because it can potentially be interpolated. But in other cases, like, hey, I sent you money, I couldn't store it on the other account, well, then it's just gone now, is obviously not an option. So it depends on the context. But in general, my advice is to create software that it embraces the fact that it potentially can't do what it's trying to do and then comes up with a backup mechanism, which can be a local dump on the file system or sending it via email as an attachment to like, hey, I tried to do this, but it didn't work. I'm going to notify somebody now and just give everything along so that it can be recovered if that's important enough to do so. Because you can't just not store it in some cases. And we did that with one of our clients, where you apply for something, and if for whatever reason we can't deal with this stuff properly and our validation failed, or some other stuff that we actually didn't expect to happen, we said, okay, we don't want this data to just vanish or create cryptic error messages that we can't deal with. We're just going to forward the fact that we can't process it the way we intended it to some administrative team and just keep the data as like a raw data entry somewhere so we can automatically process it after the fact, then recover that way.
sorry, but it will work only if all external services we use support like two-point commitment. Because if we, for example, we split it into two like atomic services, and each of them calls another external service, and if one fails but the other one was succeed, means that we won't be able to undo the stuff the external service.
That's what this Saga stuff comes in place, where you have to do the counter operation. If you already deducted the money, you cannot pretend it never happened. Then you just have to refund it.
So you don't roll back the event.
It depends, right? You cannot. No, an event is immutable. An event just happened. I cannot pretend this never happened, or I shouldn't. But I always can do a counter operation if this is necessary. So I could say like, hey, I tried to do this. I managed. Event has been written. So this is a fact now. You cannot lie about facts, or you shouldn't at least. Now the next step is supposed to happen, and this didn't work. So this fact still remains. So now I have to do something to counter this effect. Okay. So yeah.
Would it be possible and would it make sense to duplicate the conductor for large-scale enterprise projects?
So I have more than one instance?
Yeah.
Yes, you can. It comes with new sets of problems because now you have to make sure they don't run on each other's toes. But that's usually done with sharding mechanisms. So simple thing that somebody did as a training exercise was like if you deal with orders, you do every order that starts with 2, you do all the orders that start with 3, and so on, and then you scale out this way. If this is, or like has the zip code starting with this, or is this in this region, or whatever kind of mechanism that you think makes sense.
And a little follow-up question. Should they all still write in the same event bus?
That depends on how you define the same event bus. Because technically, if you use, for example, SQS or anything large in clouds, that's a routing question. And you're just going to talk that particular service. And if it's the same physical instance, or if that's a cluster that has just like various kind of nodes that you talk to, technically it's going to be all the same. So I wouldn't necessarily say yes or no. It really depends on your kind of setup and how you can potentially route things. I would probably opt for not making too much noise so that everybody sees everything. And in this example, I, as the stock service, reacts, of course, only to the command, but this conductor has to react to these kind of two things and obviously to the payment thing as well. So that's going to see all the events because it's responsible for all the events. But you could easily argue like, okay, you know what? I'm going to split this and only make the first part an event bus and the second part an event bus, and then have 3 individual conductors dealing with only that particular fragment of the process. That's a different way of sharding it. Does that somehow answer your question?
Totally, thank you.
Cool. I think you were quicker.
Just in the first approach, orchestration, so somehow orchestrator is responsible for handling client-side response. So it will handle everything and prepare the response for client. But in the Graph one, first I want to know which service will be responsible for client-side. I mean, preparing the result for the client. And what happens if we want to update something? Currently, the order service probably will be entering point, but if we want to update stock or payment, probably the payment or stock will be entering point. And we will have some application in this case. So how, and also when we scale each service, we have maybe we receive several requests at the same time. In this case, how do we handle stuff?
Okay. I'm not sure I can fully answer this because there are too many potential variables in place. In general, I would say that what happens in the background here is stuff that is literally back-end only, and the front end doesn't need to care. To me, the order placed is the final step in the actual ordering process that the front end would deal with, right? Because I ran through the checkout, everything is going to be confirmed. So payment has technically been made, but it's not being captured. So it's like the payment provider knows about this transaction, but it didn't actually freeze the funds yet, it just reserved it. So everything that happens in the process here is just purely back-end, and no front-end would actually ever see this in any direct response kind of way. Of course, when the stock has been changed, then maybe if the website has some stock counter availability, whatever kind of information for a given item, that information needs to get updated. But this is an asynchronous process, and this is just reacting on this stock reserved thing in a different way. So you can have that decide that this is part of the stock service to update the projection if you use CQRS kind of environments. Or if this is something that is then written into the database as like this is the updated thing, and then the website directly knows this. So that depends on your implementation. So you don't actually have to update anything per se if it's just reading it fresh from there.
So actually we need to somehow define some business flow. So the ordering flow, for ordering flow, the order service will be responsible for everything. And actually it will be an orchestrator for this flow.
Well, in this case, of course, each thing is responsible for its own subsection and reacts on the external events. In this thing, where I explicitly didn't place it in any of the services because it's an outside thing that just knows how the process works. But of course, the business process and the website showing it or representing aspects of it are not necessarily fully identical, right? So if you were to model the full checkout process, what you can do from the application's perspective, that's potentially a very complex beast, right? Like you have to specify your address, you want to verify the address, maybe you select it from stored previous addresses and whatnot. You have all kinds of different types of payment, you have different types of shipping things. But from the checkout's perspective, for an order to be completed, I need a address, I need a confirmed means of payment, and I need a means of shipping. If you selected it from 10 different ones, or somebody magically made it up, or it's defined hard-coded because that's the shipping method that we only support, the checkout by itself as a process doesn't really care. So the website, combining all the individual process flows, is way more complex. But it's just combining the things and then creates a result that's potentially processed by the order service. Because the order service, in my example, in my world, doesn't need to know that there is a set of addresses where they come from. It's just like, okay, you selected this address. Yeah, okay, that's the address you're going to use. And if it's a pre-existing address or something you just entered because the forms allowed you to do so, is an implementation detail of the application, of the web, whatever public-facing something. So I'm trying to push this more to the back and don't care about those details and make the actual application flow be here. The actual business flow be here, and the application flow is a different thing because that also has different reaction patterns, right? The fact that you click on a button, then wait for 20 seconds is not necessarily something you usually feel like happy with. Does that answer your question a little?
Yeah.
Okay, I guess we can.
Real world, this order flow is somehow is a simple flow, and we know everything about it. But in the real world and in the complex application, all services somehow rely to each other. And for one business flow, we need similar response from different kind of services. Maybe for one request, we need a response from service 1, 2, or 5. And another response, the entry point will be service 5, but we need a response from service 8, 9, 10. And this
Okay, so you have a distributed monolith.
it will be maybe harder for a distributed team to work on this
Sure.
geographic pattern.
But I would argue, and maybe we should take this into a more private conversation a bit, that this is more, like, as I said, a distributed monolith, and that's maybe an architectural anti-pattern if you have to talk to all these services at runtime all the time. Okay, any more questions? Yes?
If, let's say, we have the time of the world over-engineer these cases, what's the most advanced pattern that we have? Let's say we have enterprise with super low scale. This is like the most advanced pattern that we have.
Well, that's the most common one. I'm not sure if it's the most advanced one. What I would, well, maybe this already hints at it to some extent, but to me, the most logical follow-up thing to do is not have the local standard persistence anymore, but do everything in events and then have what some people might have heard, something called event sourcing in place. Because that allows the most flexible means of reacting to things, acting on things, and just forwarding things around, because you don't actually have to write everything twice or have whatever kind of nice data structure and then ship it or whatnot. It's just everything is events. And then doing only events and build things. Event sourcing has so many options that it makes a lot of things a lot easier. Of course, we have the distribution problem still in place, right? If you can't write that event to the other thing, then you still need a means to recover from that. But that's the same thing if you use, like, trying to send them using PHP mail as an actual PHP function. It's going to use send mail, which is a local CLI process. And it's going to write this to the local disk until it manages to deliver it to the actual upstream mail server. So that's a fail safe, because we don't know if the remote server is there. So nobody would try to talk to the remote mail server and realize, oh, I can't do this right now, so now I have a problem. No, you're just going to dump it to the local file and make sure that somebody else will take care of it. And with events, that's the same thing. I did my work, I'm going to emit an event, and somebody else will act on this now. And the knowledge of what that event happened means that what happens now is something that has to be written down by either this means or the other orchestration or choreography way of doing it. But it's the most flexible way that I know of, and it makes dealing with complexity a lot easier, particularly in enterprises where you don't know who is going to be interested in doing what. If you have a traditional database with, like, relational data tables and everything in the center, you're basically doomed because you can't make any changes because you have no idea who's reading this. But if you have events, you don't necessarily know who's consuming them, but you can version the events. Like, hey, I changed this particular thing. Now this is in version 2, this is different. Or we changed our software. This event is no longer being published, but that means the old ones are still there and they are still valid. So there's a lot of things that get a lot easier if you use event sourcing or event-based types of software. Whether or not that's the answer to all your problems, hey, sorry, I have no idea. Sometimes that's way overkill. Does that answer your question a little? Cool. Okay, I guess we are way over time. So thanks very much. I think there are no questions in the chat. So again, thanks for being with me. And yeah, if you realize you have more questions, feel free to connect to me or write me an email. Otherwise, I'll be around a little bit. Thank you.